I'm Sam Alcaine, the namesake of the Alcaine Research Group. And today I'm going to be talking about improving product quality and safety by leveraging some novel antimicrobial enzymes. Now this all my research strangely kind of begins with this picture. So again, as Jenny mentioned, if some of you have heard me speak before over the past couple of years for the Dairy Australia sessions, that beer kind of epitomizes a lot of my research where we're looking at fermentation of whey and producing these alcoholic beverages. It's been a main focus of the lab. Sadly, or maybe in a good way, pizza surprisingly also started another main route of research in my lab. Started with a discussion around cheese when I was lucky enough to be visiting Chris Hansen, their R&D offices in just outside of Copenhagen in Denmark. I spent a couple months with them before I was starting up here at Cornell. And they were having a discussion about the issue of browning of cheese, right? And the issue of excess lactose. And they had brought up an enzyme that they had commercialized with Novozymes called lacto-yield. It was a lactose oxidase. And basically what it was doing was it was taking the lactose that's present in milk, right? Lactose oxidase, and converting it into lactobionic acid, which then wouldn't have the Maillard reactions with proteins and cause browning. That was something they were maybe thinking about it. It was already being used in the dairy industry to generate lactobionic acid. It's used here in the US by some companies as kind of a bulking agent in some of the processed shredded cheeses. Lactobionic acid also has applications in cosmetics. It's used in moisturizers. It's also used as a bulking agent for pharmaceutical products. And so everyone was talking about lactobionic acid, but they also said that it produces lactobionic acid, and it also makes some hydrogen peroxide as part of the reaction. And that, me as a micro guy, was like, hydrogen peroxide, and that got me thinking. Right, in raw milk, we have a natural antimicrobial system called the lactoperoxidase system, right? And that's been, we don't really use it a lot in the US. In Europe, we've got a cold chain and we've got pasteurization. But I have also spent some time with the World Health Organization doing food safety. And in some areas of the world where there is not a strong cold chain, they talk about using the lactoperoxidase system as a natural system to help extend the shelf life of raw milk until you can get it processed. And so I was like, well, how does all this potentially come together? So I don't know how many people on the call are familiar with the lactoperoxidase system, but basically, right, it's in milk. It involves an enzyme called lactoperoxidase, which then takes thiocyanate, which is a compound that's naturally present in milk, and in the presence of hydrogen peroxide, right, it generates these antimicrobial compounds off of thiocyanate. Now, the thing is, where do you get hydrogen peroxide, right? Now, this system was probably, right, it's naturally there, right, because when there is some bacterial growth in the milk, right, some of those bacterial species might generate some hydrogen peroxide. It'll turn on the system and then knock them out, right? So kind of a way to keep the milk, right, fresh. Now, with the WHO method, they talk about either, adding hydrogen peroxide directly to the milk, or there are methods where you could take glucose oxidase along with glucose, add that to the milk to generate a little bit of hydrogen peroxide. But now you're adding sugar and you're adding this enzyme. But I thought, hey, well, this is lactose oxidase that Chris Hansen had mentioned. You'd be taking lactose, which is naturally endemic in the milk. The oxygen's around, and then that lactose oxidase would generate the hydrogen peroxide, and then you could use it to activate the lactoperoxidase system and generate these antimicrobial compounds, and then potentially, right, impact quality and safety of the milk, either with the antimicrobial compounds that are generated off of thiocyanate or with the hydrogen peroxide itself. And there's some benefits here, right? Because again, it uses, the lactose that's naturally present in the milk, and the lactose oxidase is an enzyme that's naturally produced by a mole. And, dairy consumers are already comfortable with seeing enzymes on the labels of their products, right? We've got, rennet, we've got lactases that we use for lactose-free milk. And so it aligns with consumer trends and might be something that could actually then be a label-friendly antimicrobial. But the question was, how well does it really work in dairy systems? And so a few years ago, we started trying to play with this. We began looking at how this system would work to control Pseudomonas. Pseudomonas species are one of the most common spoilage bacteria found in fluid milk products. And so we wanted to see how it would work against that. So what we started off with was a pretty simple set of experiments where we took, UHT milk. All right, so, all the background microflora had been killed. And we added in a Pseudomonas fragi cocktail. And then we looked at different levels of lactose oxidase. So we inoculated around 10 to the 5 CFU per mil. We had 6 different treatments. So here you look at the top, we have this lactose oxidase at a very low level, 0.012 grams per liter. We had then the addition of thiocyanate and lactoperoxidase. Is this the, yeah, and lactose oxidase. Again, the lactose oxidase is at a little higher level. So this is lactose oxidase by itself. This is with the lactoperoxidase and thiocyanate. And this is lactooxidase at a little higher level, 0.12 grams per liter. Then in combination with lactoperoxidase enzyme and thiocyanate. And then finally, high level lactose oxidase, and then lactose oxidase in combination with lactoperoxidase and thiocyanate. And basically the takeaway here was that what you see is in our control with the Pseudomonas, right? The Pseudomonas grows out pretty well at refrigeration temperatures, 6 degrees C, with nothing to hold it back. Low levels of the lactose oxidase with and without the lactoperoxidase system didn't really hold things back, but at these moderate levels, 0.12 grams per liter and 1.2 grams per liter, we were able to prevent the outgrowth of Pseudomonas and really knock it down, right? So that was pretty interesting, saying, all right, we have a mechanism to control Pseudomonas. Then we wanted to kind of understand how did the components of the lactose peroxidase system interact with one another. So we played around with thiocyanate levels, right? Because that's the compound that's generating, right, the antimicrobial compounds. And so here we worked at looking at, again, our control with our Pseudomonas cocktail here. Then we looked at lactose oxidase in combination with thiocyanate at 3 different levels, 14 milligrams per liter, 140 milligrams per liter, and 1400 milligrams per liter. And then with the addition of lactoperoxidase. So this is the control here. The first 3 bars here are the lactose oxidase with the thiocyanate at increasing levels, and then with lactoperoxidase at those increasing levels. And then we saw some kind of surprising things here, right? So the lactose oxidase with any of the thiocyanate levels did a really effective job of knocking down the Pseudomonas and preventing its outgrowth, right? We didn't see detectable outgrowth at some of these higher levels by day 7. Whereas interestingly, once we added in the lactoperoxidase enzyme, we saw kind of not as good efficacy of this entire system. And what we think is going on here is, as we went into the literature, at the higher, what they've noted is that at higher levels of thiocyanate, there is some inhibition and competition with the enzyme's active site when there's high levels of thiocyanate, and so that might be what's going on there. And so basically, what it looks like is, if we're going to have lactoperoxidase in there, that low levels of thiocyanate of 14 milligrams per liter, which is actually the level of supplementation that the WHO recommends anyways when you're working with the lactoperoxidase system, is sufficient. And that high levels of thiocyanate don't really help the lactose oxidase enzyme by itself, right? So we can keep it pretty simple. And then what we wanted to do, that was all in UHT milk, so there was no background flora. We decided to put it in pasteurized milk where all the LP, the lactoperoxidase, isn't completely inactivated, so we don't have to add it back like we did in those sets of experiments. And so here again, the takeaway, we also worked with some lower levels of lactose oxidase and then we had worked with below to see how low we could take it. And basically the takeaway was kind of what we saw earlier, that at this level of 0.12 grams per liter, in the presence of with a little supplementation of thiocyanate or even by itself, that the lactose oxidase here is able to hold down the Pseudomonas effectively. And so it's something then that could potentially be used as a way to control for Pseudomonas in milk. Now, the question is, we kind of start talking about raw milk. How does this just work in a whole raw milk system? So then our next step there is we source raw milk from our dairy here on campus. And what we did here, looking at the chart on the right here, is we had our control milk, right? Raw milk, with nothing else done to it. Then we had raw milk where we added the lactose oxidase enzyme completely by itself at the 0.12 grams per liter. Then we followed the FAO method where we added 14 milligrams per liter of thiocyanate and 30 milligrams per liter of sodium percarbonate, right, to generate that hydrogen peroxide. And then our last treatment was lactose oxidase at the 0.12 grams per liter with the 14 milligram per liter supplement of thiocyanate. And that's also used in the WHO method. And then what you see here is that, right, our control, right, we begin to see growth, right, starting at around, 6 hours, and it grows out to around, 7 CFU by 24 hours. And so here, right, we're probably passing the spoilage mark. The lactose oxidase by itself in raw milk, right, which has, a flora broader than Pseudomonas, it's the natural microbes that are present in the milk, doesn't do a whole lot of knocking them back and preventing the outgrowth of those organisms. Here's the WHO method in the diamond. Here you see it slowing down, right? So you get a little extended shelf life with your raw milk using this WHO method. And here, right, we're storing the milk at ambient temperatures, 21 degrees C. And then if we do the lactose oxidase with the thiocyanate, we definitely see, right, a reduction in the outgrowth of the natural microflora in the raw milk, which means, right, we could potentially then use this in areas of the world, right, where there is not a cold chain, and we want to keep down, the microflora outgrowth before it gets to a processing facility to give us a little bit more time. And if you look at the data here, right, we significantly increased the lag phase of the microbial outgrowth versus the control. And there was a significant difference in the final counts that we reached after 24 hours with the lactose oxidase thiocyanate treatment versus the control, and really versus any of the other treatments. And when you're looking at, well, lactose oxidase generates lactobionic acid, we don't see a major impact here on the pH of the product after 24 hours, right? We're only at 6.67 here with the lactose oxidase thiocyanate, and our control was at 6.68. So there wouldn't be a major impact on the sensory properties of that raw milk before it gets processed. So that was exciting. Then we were curious, well, how does this hydrogen peroxide generated by lactose oxidase impact other microorganisms that might be relevant for dairy? So we did a quick screen that we published in the Journal of Dairy Science back in 2019, where we basically did this diffusion assay with different organisms. So, right, E. coli, Listeria monocytogenes, Staph aureus, Salmonella, again, Pseudomonas fragi, and a mold, right, Penicillium, a very common spoilage organism in dairy products. And we had different levels of the enzyme added to each of these wells, right? We incubated this overnight, and then we measured the zones of inhibition. And you can see we incubated them at quite high temperatures, right? So this is, pretty favorable for that micro growth. And what you see is that for some of these organisms, there is some inhibition. Sometimes that you require higher levels of the enzyme, but we do see zones of inhibition for E. coli, definitely for Listeria when it's at refrigeration temperatures, a little bit when it's held at ideal growth temperatures, some for Staph. We talked about Pseudomonas, quite effective against Pseudomonas, and then some a little bit against the Penicillium. You'll also note here that on our wells, there's this little cavity here. So we wanted to confirm that the inhibition that we were seeing was due to the hydrogen peroxide activity and not due to acidification by the lactobionic acid. And so here we spotted catalase on the wells, and right, which then breaks down the hydrogen peroxide and shows, right, that what's going on here is hydrogen peroxide activity, not acidity. So that kind of laid the groundwork for, all right, there is some other areas to kind of look at, you know, what lactose oxidase could do in dairy systems. So what else could we see? So one of the areas that was a natural jumping off point with our first set of research around Pseudomonas was an area around UHT milk. So UHT milk makes up around a little over a quarter of all milk consumed globally. Now, one of the benefits of UHT milk, right, is that it's shelf stable. So, you know, once you processed it, it's very stable, doesn't require a cold chain. So it's easy to get to market, get to consumers in hard to reach places, right? And there's a lot less spoilage, a lot less energy usage to maintain that milk. Now, one of the defects that we see in UHT milk is called age gelation. And so we see this coagulation over time in UHT milk, and this is due to proteolysis of the protein. And that proteolysis is sometimes driven by either high plasmin levels in the initial milk that's being processed, or and that plasmin, right, is pretty heat stable. So if it's at high levels, can impact the finished product even after UHT treatment. But then there's also heat stable proteolytic enzymes that are produced by bacteria, especially if they grow to high levels in the raw milk before processing. And again, one of those bacterial species that is responsible, well, mainly responsible for these heat stable proteases is Pseudomonas. And I don't know, you know, all the regulatory systems there, requirements in Australia, but here in the US, right, when you think about our dairy processing chain over here, right, we get our fresh milk from the farm. It could be sitting at a tank in the farm, you know, for 24 hours before pickup. It goes into that milk tanker, has to be taken to the dairy processing facility, and then it can sit in these raw milk storage tanks for up to 72 hours. And I've heard horror stories where sometimes, right, the plants are running behind, and these milk tankers can actually be sitting outside the processing facility for, you know, anywhere from 6 to 12 hours before they actually get, you know, unloaded and put into these tanks. And so there is quite a bit of time here, you know, 72 to 48 hours where you could see growth of psychotrophic organisms like Pseudomonas in this, right, where they might get to levels where they produce heat stable proteases that then, even though, you know, they'll get knocked down by pasteurization, those proteases will then stay active and impact the finished milk. So, you know, how long are we in this danger zone? And is there a possibility then to apply lactose oxidase to control Pseudomonas outgrowth and prevent this type of defect? And then stop, you know, age gelation, because no one is going to want to see chunky milk when they're pouring out their UHT milk. And if they see that experience, they may not want to buy it again. And so in our lab, we went through a set of experience where we kind of looked for strains, Pseudomonas strains that produce heat stable enzymes or heat stable proteases, and then looked at the ability of lactose peroxidase to control their outgrowth. So here, just quickly, you know, we have here at Cornell, we have the food safety lab and the milk quality improvement program, which has been sampling dairy products here in New York State for now over 30 years, right? And we have a pretty wide library of different Pseudomonas species, but they've never been characterized for their ability to produce heat stable proteases. So we went through and we screened 3 different species, fluorescens, fragi, and ludensens, to see whether or not these isolates had proteolytic activity and whether or not those proteases were actually heat stable. You can see the sources of some of these isolates, right? Some were from cheeses, some were from the environment, some were from UHT milk. And you'll see that all our fluorescence isolates that we have in the lab and all our ludensens do produce heat stable proteases. Not all the fragi do, but some do. And then what we ended up doing is selecting 2 strains from each of these different species to make a 6-strain cocktail that we then use to challenge our milk later on for the rest of these experiments. All right. So what we did as an initial test just on the benchtop is we took already processed UHT milk and we either spiked it with that cocktail of Pseudomonas at basically the worst case scenario. So here in the US, our requirements around total plate count for raw milk is we have, if it's a single source, there's a limit of 100,000 CFU per gram or per milliliter, sorry. And then if it's commingled milk, there's a limit of 300 CFU per milliliter. So that's kind of where we targeted it as our worst case for Pseudomonas. You added that to the milk by itself, and then with this lactose oxidase at this 0.12 gram per liter, this level that you've seen before in our previous experiments, and then we incubated it right at 6 degrees C, and we measured the outgrowth of Pseudomonas. When Pseudomonas get over that worst case 96-hour time point, and when Pseudomonas gets to around a level between 10 to the 7 CFU per mil, 10 to the 8 CFU per mil is when it starts to produce those heat stable proteases. And so, if you have already, a high load of Pseudomonas coming in from the farm, it's able, right, to grow out to concerning levels, right, within 48 to 72 hours. So there's a potential danger zone in the dairy supply chain here in the US, depending on the quality of the milk coming in. And then here you can see when we add the lactose oxidase, it knocks down that Pseudomonas and we don't see that outgrowth. Now, what's the impact of that enzyme on pH? It does drop the pH down a little bit more than we would see, right, with the Pseudomonas in the milk, but it's not that much more, right? We're here looking at the end of 4 days, right? The Pseudomonas is around a little above 6.5, and here we're around 6.3.5. So not a big difference. Here at day 4, here we just show that, if we do a heat treatment like a pasteurization step to inactivate the enzyme's activity does stop, right? We don't see increased acidification. So once it gets to pasteurization, we're done. We don't have to worry about the enzyme over acidifying anything. It's done what we wanted it to do, control the lactose, control the Pseudomonas. Then here looking at, well, then is there an impact on, then age gelation, right? Coagulation. So here what we did, it's a little complicated of a graph. What we did is that, right, we took the milk, right? It was either raw milk, nothing done to it, raw whole milk. It was our control, which is the whole milk with the Pseudomonas added to it, either stored for 0 days, 1 day, 2 days, 3 days, or 4 days at 6C before UHT heat treatment. And then, right, the last one, this middle one, is that milk with the Pseudomonas treated with the lactose oxidase, held for 0, 1, 2, 3, or 4 days. And then at the end of each of those days, we heat treat it, right, use the UHT heat treatment, and then we monitor it over 4 weeks. And what you see here, right, is everything at, that was held for, not held at all or held for 1 or 2 days, right, with or without the Pseudomonas and with or without the lactose oxidase. We didn't see any increase in the diameter of the particles, right? So we didn't see coagulation. But, right, if the milk was held for 3 or 4 days before UHT processing and it had Pseudomonas in it but no lactose oxidase, you do begin to see gelation of the milk, right? But you don't see it when we treat it with lactose oxidase. So there again, hey, it shows, right, that we could prevent protease-induced coagulation by controlling Pseudomonas outgrowth. And I see a little chat box. Oh, Kim's just saying that he's got to check back in. We'll see Kim next time then. We'll continue here. Actually, unfortunately, I gotta do one quick close the chat. Sorry, my chat box is now in the middle of my screen here, so I gotta get rid of it. There we go. All right, back. So now the question was, well, that was in UHT milk. What happens in real raw milk, right? There's background microflora, all these kind of things. So now we took this system and we tried it out. Well, what happens if we have raw milk and then we contaminate it with these protease producing Pseudomonas? Is the lactose oxidase, what levels of lactose oxidase are able to control it. So here in this graph on the left, what we have going on here is this, this curve here with the dotted lines is the enumeration of raw milk inoculated with that Pseudomonas cocktail, right, at around 10 to the 5 CFU, and its outgrowth over time, okay? And we keep it in all these other windows as a comparison, okay? Then here is our raw milk in the solid line here with no Pseudomonas cocktail added to it. So you can see, right, our starting background microflora levels are quite low, a little over 10 to the 3 CFU per mil. And then this is how that microflora grows over time. Now this is that same raw milk, still no cocktail, Pseudomonas cocktail added to it, but treated with 0.12 grams per liter lactose oxidase. And it just shows that at these refrigeration temperatures, it, right, prevents the outgrowth of that background microflora, right? Now here is then the examples of where we have the raw milk and that Pseudomonas cocktail is added at the 10 to the 5 CFU per gram. And then these are the treatments: 0.12 grams per liter lactose oxidase, 0.12 grams per liter lactose oxidase with the thiocyanate. And you can see the difference, right, that adding that little supplementation of thiocyanate, the 14 milligrams per liter, does to this. Though the lactose oxidase by itself does slow the growth of the Pseudomonas at this level. At a 0.24 grams per liter, we definitely see inhibition of Pseudomonas outgrowth with and without thiocyanate. And then at 0.6 grams per liter, it's very significant, okay? Now, what does that do to the pH? Over here on the right-hand side shows the pH curves. Now, in this case, the dotted line is the pH of the raw milk by itself over this storage time when it doesn't have the cocktail and doesn't have lactose oxidase as a reference. And then here you can see this is raw milk with the cocktail. That Pseudomonas outgrowth over time causes a little bit of a drop of pH. Here it is with the lactose oxidase, you know, not that much more at the 0.12 grams per liter with and without thiocyanate. A little bit more of a drop with 0.24 grams per liter, but not that big. There is a bit more of a drop with the 0.6 grams per liter, but really, right, if you're looking at it, you could use 0.24 grams per liter lactose oxidase, not have a major impact on the pH of the milk, but definitely hold back the outgrowth of the Pseudomonas. Now, does that result in prevention of the age gelation? And basically the story is yes, right? So here we are now monitoring the gelation of the milk over time. This is the milk stored at 3 days, milk stored at 4 days before UHT processing, and then following each of those milks over a 5-week period. And we held the milk at 30 C, which kind of speeds up any potential coagulation. And what you see here is that pretty much in all these treatments with the lactose oxidase, we don't see coagulation. When the cocktail is there by itself, we definitely see coagulation. And then here, if you hold the milk for 4 days, again, we see coagulation when the cocktail is there by itself. We do see a little bit of coagulation here with the low level of lactose oxidase treatment with no thiocyanate supplementation after 5 weeks. And if you go back here to this graph here, you can see after 4 days, right, with this 0.12 grams per liter lactose oxidase treatment, that the Pseudomonas was able to grow out pretty high, and not surprisingly then produce, right, was able to produce at those levels a little bit of protease. But at a little higher level, right, we're able to control it. So then the question was, well, how does this work when things are scaled up? So we went to our pilot plant facility and we decided to scale up the process. What we did then is basically did that same treatment. We had a control that was just raw milk, nothing added to it, a positive control, which is raw milk with the cocktail added to it. And then to keep it simple, one addition, we added lactose oxidase at the 0.24 grams per liter treatment level. We thought about doing it with the 0.12 grams per liter and the thiocyanate supplementation, but it seemed like it was easier just to do one ingredient add, making it the enzyme. And then what we did is after storing it, This is we treated the milk with our little microthermics unit here, and these are the processing conditions. And this is again kind of what we saw. Well, not kind of, this is what we saw. So here is our raw milk by itself, enumerating, right, what were the cell counts. Again, our raw milk is pretty clean here, coming from the dairy on campus, only 10 to the 3 CFU per mil background flora. And this is how that flora grew out over 3 days. Then this is that same raw milk where we added the Pseudomonas cocktail. You notice here, interestingly, we didn't see as much outgrowth as we had at the benchtop scale. These were in 5-gallon containers. And then here is with the lactose oxidase treatment at 0.24 grams per liter. And you saw that, we didn't really see much outgrowth at all, any significant outgrowth of the Pseudomonas. This is the impact on pH over those 3 days, right, kind of in the raw milk storage tanks. We do see a decrease in pH with the lactose oxidase treatment because of the lactobionic acid. But it's not that much lower, right? We're 6.8 is where we started at, and we get to around 6.7, whereas the other 2 treatments stayed at just below 6.8. And then, right, we heat treated all those samples, and then we monitored them for coagulation over time. And this time we did it over months at low temperature. So this is like 21 degrees C, and this is 30 degrees C. And again, what you can see here is that because the lactose oxidase was effective at controlling the outgrowth of the Pseudomonas didn't grow to a level where there was protease production, and therefore we don't see coagulation over 6 months. Whereas if you didn't control it, we were able to see coagulation. So this is a method, right, to control Pseudomonas in raw milk and prevent this age dilation potential in UHT milk. And then this is just a visual representation over those months of where you can see what that age dilation looks like. Right here on the right is the milk with the Pseudomonas and no lactose oxidase. This is the milk treated with lactose oxidase, and this is our raw milk, right? And you can visually see that difference. And then interestingly enough, right, we noted that after those 3 days of storage in the raw milk, that the pH of the lactose oxidase treated sample was a bit lower than the raw milk control and the raw milk with the Pseudomonas. But over storage time, right, that UHT treatment inactivates the enzyme, but there is interestingly some drop in pH by the control, which had the Pseudomonas grow out in it over time. And so really over the shelf life of the product, our lactose oxidase treated UHT milk is closer to the raw milk control pH than the one that has Pseudomonas outgrowth in it. So it's actually still a better product. So we think there might be some potential applications for using this lactose oxidase to control raw milk quality before processing. Now, some other areas that we decided to get into. Again, we were interested in what are other areas where Pseudomonas is a potential issue in dairy products. And so I don't know if some of you are familiar with, in mozzarella, there is a blue coloration defect that happens in mozz that is due to the outgrowth of Pseudomonas over time in the finished product. And it makes, right, the mozz go blue, which isn't great. And so we decided to look at what would happen if we applied lactose oxidase to the surface of mozzarella and then challenged it with Pseudomonas forensens, which is one of the Pseudomonas that are responsible for that blue discoloration in mozz. And so here is just some work that we published in Food Control, where we took fresh mozzarella. This mozzarella was produced with the direct acidification method, right? So they're adding acid to the milk, right, to create the curd. They're not using a culture. And then we spotted on lactose oxidase. We cut it up in little cubes. We spotted lactose oxidase on the surface, and then we spotted on this Pseudomonas forensens. And what you see here over here is after 16 days, this is a sample of the motts that didn't receive the Pseudomonas and didn't receive the lactose oxidase. You see it's a nice, right, nice kind of whitish color. Then here's a sample that's challenged with the Pseudomonas, but no lactose oxidase. And then these are increasing levels of the concentration of lactose oxidase in I think it was a 100 microliter sample that we added to the surface of the cheese. And you can see at low levels, right, the lactose oxidase isn't quite strong enough to hold back the Pseudomonas, but at 0.12 grams per liter in the surface application, in some cases it's able to. These are triplicates here, and then these are technical replicates. And then at 1.2 grams per liter, it is able to prevent, right, the development of this blue discoloration in the motts. And I'm not going to go into all the numbers, but we did also image analysis of the, of the area of the blue development, and it's a significant difference in that. We also looked at it in the other types of mozzarella that's acidified by culture. And this, you can already see from the images, is a little bit messier. This mozz doesn't really like being held for 16 days of a challenge study. But here's the same thing where, again, here's that culture acidified mozzarella after 16 days with nothing added to it. This is that culture acidified mozzarella with the Pseudomonas spotted on the surface, and you can see that blue defect. It's not always consistent all over the surface of the cheese. Sometimes it makes it look green, and sometimes you see that characteristic blue. And then here it is with the different levels of lactose oxidase. And so you do see a difference in the way that blue discoloration develops over time. I will say that, because of the background color change of the cheese, it made it much more difficult for the, when we were doing the actual color analysis, to find a significant difference, but kind of visually you see that directionally it's there. So it's maybe not as effective in culture acidified cheese, maybe needs a little bit more work to understand what's going on there, but definitely effective in the direct acidified mozzarella applications. And we've also done some other work looking at this in other cheeses, and there's some promising results there. Now, another area in dairy spoilage that we decided to look at, right, was yogurt. There's another, right, or where we see spoilage that leads to color changes that we don't want. And the question was, well, could lactose oxidase, prevent the greening, right, with mold? And so we went back to our library. We pulled out 5 different species of penicillium, right, again, which is a very common mold spoilage in yogurts. And you can see these are the sources where we got them from. And we did a pretty basic experiment where we made, lab scale yogurt in these little, I think these were, want to say that they were 1 mil wells to make yogurt. And so basically then what we did is we had a well where we had the yogurt with no mold, no lactose oxidase, a well where we challenged it with the mold, and then 4 wells where we had increasing levels of lactose oxidase applied to the surface of the yogurt. And what you can see here is that, yes, topical application of lactose oxidase to the surface of the yogurt can inhibit mold outgrowth. Now it varies, the efficacy varies depending on the mold species. So you can see here with the cumbens, right, it's very sensitive to the hydrogen peroxide that's produced by the lactose oxidase, and we don't see any outgrowth at all. Whereas Penicillium commune, right, is a little bit more resistant compared to the other ones, right? It can grow out and overcome 0.48 grams per liter surface application of lactose oxidase. And then the other ones are kind of intermediate. Now, I will note that this was after 2 weeks of storage at 21 degrees C. So it was a pretty aggressive challenge temperature, right? And so we'd expect that, the ability of these molds to grow, right, would be, slowed under the refrigeration conditions that we would typically hold these yogurts, but it's a promising application. Now, what did the lactose oxidase do to the pH? Again, that's something to watch out for. Here you can see the squares here are the yogurt by itself. And then this is the yogurts with increasing levels of the lactose oxidase if it's applied to the surface. And there is a bit of a pH drop over time that might or might not be an issue. But again, one of the things to remember here is that this yogurt was stored at 21 degrees C. And so the impact of this pH reduction might not be as severe if we were holding it at the common refrigeration temperatures that we store yogurt at retail. And then another thing we wanted to see was whether or not there was any impact of the lactose oxidase on the cultures. And so here we enumerated the cultures in the yogurt. We just bought commercial yogurt and added the lactose oxidase to the top. We also added a little bit of catalase because we were trying to see if, when we went to go enumerate these lactic acid bacteria, whether or not adding catalase and leaving the lactose oxidase active in the sample, would that actually make it more difficult to enumerate the lactic acid bacteria, but doesn't seem to be. So we did see a decrease in the lactic acid bacterial counts, right? So they dropped from around 10 to the 8 to around 10 to the 6. That's still levels sufficient for a live and active culture claim here in the US, but it's something to watch out for. But again, the caveat being here, right, we stored this at a high temperature, and maybe if we did this at a lower temperature, we may not have seen as big of an impact on the lactic acid bacteria. We'll see. I have seen some studies where they had previously looked at glucose oxidase too as a natural oxygen scavenger in yogurt, and lactose oxidase might be able to play a role there. They did that work at refrigeration temperatures, and that might be something we look at in the future. So that kind of concludes our spoilage research, right? We're always interested in preventing waste. When we had done that initial screening of microorganisms that are relevant to dairy on those plates to see, could lactose oxidase inhibit them, we did see some promising results in Listeria. So we wanted to dive into that as well. And so here it's kind of right, could we control Listeria and prevent it from maybe adulterating our dairy products? So we first looked at the effect of lactose oxidase on Listeria monocytogenes in milk under a couple different conditions. Again, first kind of, very basic, lab benchtop conditions where we just took UHT milk. All right, so no background microflora, and we inoculated it with a low level of Listeria monocytogenes. We used a cocktail that we have in the lab. And I'll get to some of the questions later on. In the lab that were from outbreaks related to cheese. And so here we inoculated at just shy of 100 CFU per milliliter. And then we inoculated with then we added these different levels of lactose oxidase, much lower levels, right, than we had used in some of our previous experiments. And then we incubated at 6 degrees C, and we monitored the milk for 21 days. And you can see right here, the Listeria, right, with no lactose oxidase was able to grow out, right, no inhibition there. But that actually all 3 levels of this lactose oxidase were able to inhibit Listeria outgrowth. We tried it then with a little bit higher of a challenge load, right? Hopefully not something you would see in milk, but just shy of 10 to the 4 CFU per mil. And again, what you see is that over time, again, these levels of lactose oxidase were able to inhibit and then knock back the Listeria over 21 days at refrigeration temperatures, which was pretty promising. When we look at, well, what's the impact of pH? And here you can see right here's our control, right? The pH stayed pretty stable over time. But even with these treatments of lactose oxidase over 21 days at refrigeration, the drop in pH wasn't that huge, right? So there's a potential application here, right? If there's some incidental contamination with Listeria post-pasteurization, it might be able to knock them back. Now that's in UHT milk, right? In real world, right, we're worried about Listeria in raw milk most of the time, right? Because it can contaminate the milk. So here then we did some studies where we looked at sourcing raw milk, again, from our dairy here, challenging that with Listeria monocytogenes, and then looking at outgrowth over a week. Here we looked at, lactose oxidase with and without thiocyanate supplementation. And here you can see, again, over time, after a week, we do see some outgrowth of Listeria in the raw milk. We do see outgrowth of Listeria with the lowest level of lactose oxidase that we tried here, 0.12 grams per liter. But as soon as we supplemented it with thiocyanate, or if we went to slightly higher levels, right, we were able to prevent, right, the detectable outgrowth and actually knock it down, right, of Listeria monocytogenes in raw milk. So potentially, right, this might be something we might want to consider for raw milk treatment. And again, here it is at a higher load. And again, you know, the takeaway is basically the same here. That if we add a little bit of lactose oxidase to raw milk, and we're probably not going to keep raw milk and be drinking it for more than a week, we can hold back Listeria monocytogenes and even knock it down. And right, when we're talking about contamination with Listeria in the real world, it might be much lower levels than this, right? And then there, you know, we might then prevent the lactose oxidase might generate enough hydrogen peroxidase, knock down the Listeria that we won't see an impact on public health. And again, what's the impact on pH, right? At those levels, you know, it's not that big, right? The control here is at 6.68, 0.12 grams per liter treatment of lactose oxidase with thiocyanate supplementation. Not really a drop at all, but we saw, right, that it was able to hold back the Listeria monocytogenes. So this might be a potential, you know, additive we might want to consider using in raw milk. Definitely need to do some more work to see the impact on Listeria, but it's promising. And then the other that we wanted to look at was, all right, well, what about cheese? We have issues, right, with Listeria contamination in cheese. I don't know how big Hispanic style cheeses are in Australia, but they are becoming quite popular here in the US. And one of the big challenges with Hispanic style cheeses like queso fresco here in the US is that it is, right, a very high pH and very high water activity. So there isn't a lot, and it's not acidified with cultures. There's really not a lot preventing Listeria from going gangbusters in that type of cheese. And we regularly see recalls here in the US because of Listeria contamination in these cheeses. So we thought, well, maybe we could apply lactose oxidase in these cheeses and see what happens. And so here we looked at two different contamination scenarios, right? One where, you know, Listeria monocytogenes comes in with the raw milk, right? And then maybe we add the lactose oxidase or lactose oxidase with thiocyanate to the raw milk itself. Then we do the cheese make, and then we hold that cheese over time for 21 days at 6C and see, you know, if we see Listeria outgrowth. And the other potential, right, for Listeria monocytogenes contamination is when we've already made the cheese, so surface contamination of the cheese. So in this case, right, we take the milk, we make the cheese, and then we contaminate the surface of the cheese with Listeria monocytogenes, and we add lactose oxidase or lactose oxidase with thiocyanate to the surface of the cheese, and then see if we see outgrowth. And so looking at that first scenario, here is cheese where we inoculated the milk, the very low level of Listeria. So the milk was inoculated with 1 CFU per 100 mils of Listeria. And then we made the cheese. Well, then we added the lactose oxidase and we made the cheese. And then here you can see when we, at day 1, when you make the cheese, right, because of the concentration, right, and the time of the cheese make, Listeria has already made it to around 10 CFU per gram in that cheese. And then you look at it over time, that Listeria is able to grow out in the control cheese. And then in the cheese that was made with the milk treated with lactose oxidase, we see that, you know, there was maybe a little bit of outgrowth at this 0.12 grams per liter, but no outgrowth at the 0.6 grams per liter. And then we see kind of that same story here if we went with a higher load. So here we had a milk coming in with a load of 10 CFU per gram, or 10 CFU per milliliter in the milk, and we added the lactose oxidase, readily see outgrowth in the cheese. And then here we see again that the lactose oxidase is able to retard some of the outgrowth and then completely knock it back. So that's promising with that cheese, but we'll talk a little bit more about the impact on pH, which is a little bit more significant here. And then we went to the second scenario here now where we're looking at surface contamination of the cheese with Listeria monocytogenes. And so here, what we did here is we made the cheese, And then we applied lactose oxidase to the surface with or without thiocyanate supplementation in the liquid. So it's a small amount of lactose oxidase liquid, right? Because it's only like 100 microliters to the 5 gram surface of the cheese. And then we challenged the cheese with an inoculation that would achieve 2 CFU per gram total of that cheese. And again, what you see here is that over 28 days, we eventually see outgrowth of that listeria when there's nothing holding it back. But at these, a little higher levels, but 0.6 grams. And you got to remember, this is 0.6 grams per liter, but it's 100 microliters applied to the cheese. So it's really a small amount of lactose oxidase that's applied to the cheese is able to hold back the outgrowth of that listeria. Now, when we go with a higher load, so here if we added an inoculation of listeria that's 200 CFU per gram, which is really high, right? This is like a catastrophic contamination event from the environment. What this tells us is that, if you've got horrible hygiene control, lactose oxidase isn't going to help you eventually, right? Because it may not have outgrown to the same levels as the control, but it's pretty high and it's going to cause disease, right? But at low level, incidental levels of listeria contamination from the environment, the lactose oxidase use on the surface might actually be able to help you out and control, right, that kind of incidental contamination, and then reduce the amount of listeria outbreaks that we see. Now, on the pH side of things here, is a little bit more impactful on the cheeses than it was in the fluid milk in the work that we had done before. So here you can see at the end of the 28-day period that we were looking at this, the treatments with lactose oxidase versus the control were quite a bit lower. And so there is a little bit of a question that we know that, when listeria finds itself at a pH below 6, while it can survive, it does begin to drop off. So that might explain some of the drop off that we saw here, right, in this study. And so that's something to think about when making the cheese with milk treated with lactose oxidase. Now, when we added the lactose oxidase to the surface of the cheese, we didn't see as big of a drop in the pH, but we were able to see that we were able to hold it back if there was a low level of listeria contamination. So this might be, again, a potential treatment to help kind of control listeria in cheese. And so that's kind of the work that we've done, that we've had published out there. What are we, doing with lactose oxidase? When I sat down and I had that pizza with Chris Hansen, I never thought that we would be doing so much work on lactose oxidase over the last 4 years. But there are still things that we're looking at. So we have a grant, a group of us here at Cornell, looking at intervention strategies for organic dairy, particularly organic milk, to control spores, because there's a limit of the type of sanitizers and practices that we can apply in organic milk production, in opposition to traditional milk production. And so one of the things that we thought was, well, maybe we could use lactose oxidase, because in the regulations here in the United States, there is a carve out for the use of enzymes that are derived from molds in organic products. So we could use it as an organic friendly antimicrobial treatment. And so what we've done right now, it's still pretty early on in our going, is that we did inhibition assays to see whether or not lactose oxidase could inhibit the outgrowth and germination of different spores, whether they're aerobic or anaerobic spores. And so you see we did a battery. Just quickly show you a quick picture of what those inhibition assays look like. And so we measured those zones of inhibition, and you can see that some spores where lactose oxidase is actually pretty effective at inhibiting their outgrowth, whereas other spore species like Bacillus, Bacillus cereus, Bacillus subtilis, are not really impacted by the hydrogen peroxide produced by the lactose oxidase. But there might be some applications for cheese products. Here you can see that things like Clostridium tyrobatiricum, which is responsible for late blowing in cheese, right, is impacted, can be inhibited by lactose oxidase. So we're going to go forward and we're going to see, well, what happens if we make cheese with lactose oxidase, and then we challenge it with Tyrobutyricum. Do we see a difference in late blowing in those type of cheeses? And then this might be a natural enzyme that we could add to those organic cheeses to prevent, and even non-organic cheeses, to prevent late blowing in cheese. And we might look at, again, at some of these other, spore formers that have impacts in dairy powders and things like that, and see what happens. But pretty early going right now. And then the other thing is we're looking at, how do we, the challenge with lactose oxidase is once you add it to the milk, right, there's lactose present, if there's oxygen ingress, we're going to see production of lactobionic acid and increased acidification. And if you don't have something like a heat treatment, you're not going to be able to inactivate the enzyme. So we're looking at, can we use encapsulation as a means to, right, sequester the enzyme, and then, we could treat the milk with the beads that have the enzyme and then pull the beads out and then remove the lactose oxidase and stop the acidification. So we started some work where we are entrapping lactose oxidase in alginate beads. And so this is my technician's finger over here holding one of those little beads. This is what those beads look like. And then you can see we can add those beads to milk, right? Treat the milk and then strain those beads out and then see what happens to the milk. So we've just really, this is stuff that we've just started this January. So we're really early on in this work. What we did is, right, we added the beads to milk for 24 hours. Then we strained out the beads, and then we monitored the milk for another 24 hours to a 48-hour time point to see if we continued to see acidification, which was indicative of the lactose oxidase then not being entrapped in the beads. And what you can see here is we also did beads with different levels of lactose oxidase in the initial substrate that we used to make the beads. So 100% lactose oxidase in that substrate, 10%, 5%, and then none. And the good thing that we saw, right, is that no matter what level of lactose oxidase we used in making the beads, once we pulled the beads out of the milk, we didn't see a significant increase in pH or a significant decrease in pH over time, which suggests, right, that we were able to remove the lactose oxidase effectively. And we also looked at this where we titrated, we did titratable acidity to look for the development of lactobionic acid, and the same story there, right? We didn't see increased lactobionic acid production after we removed the beads after that initial 24-hour time point. So now what we're going to do is we're going to look at milk with Pseudomonas and Listeria, and then see if we treat it for the beads for a certain amount of time, and then we remove the beads. Do we see a decrease in those microorganisms, and is that decrease maintained, or can those microorganisms now, do they just grow right back once we remove the lactose oxidase from the milk? And so that's kind of what we're doing. Happy to open it to questions. I see there are some questions in the chat box, so I guess I will start with those. We got a couple here from Ian, where he notes, you and your team are completing some of the, thank you, most interesting and practical dairy research going on right now. Is it possible for Australian dairy companies or research organizations to work with your team, either using a fee-for-service model or with joint research projects? And yes, we do this with companies from all over the world. We would definitely be open for fee-for-service, where you send us, we set up an experiment and you access to execute it, and we do it for a set fee, and then we return the results. And we're also open to more intimate research projects on dairy. So please reach out. Happy to do that. Another question from Ian, interesting findings, wonder about the regulatory likelihood of supplementation with thiocyanate here, right? Yeah, that is a good question, and that's why we looked at the system with and without thiocyanate supplementation. And we do see inhibition, right? You need a little bit higher level of lactose oxidase, but you could get there, right, with lactose oxidase by itself. So that is something that needs to be thought about on the regulations for your area. Ian also asked another question around, lactose oxidase supplementation at 0.12 grams per liter. Is this going to be economically practical when adding it to, 20,000 liter hauls of milk? And I think that's a question for Chris Hansen. I think one of the things here is that right now lactose oxidase is a pretty niche enzyme, and so there's not a lot of demand for it. But if there's a high demand and you scale up the production, right, then the production costs are going to go down, and the economic cost of that enzyme will go down. And then, right, we're looking at scenarios where we might be able to entrap it and then reuse that enzyme. That might also help reduce those costs. When we're talking about it in, like, say, the cheese, the surface application, those, at the end of the day, right, it's a very low level surface application. So the total amount of lactose oxidase actually involved in the cheese is quite low, and those are probably quite economical. And then Jenny asked us a question here. Your team is obviously still investigating lactose oxidase. Is it available from Chris Hansen in any form, or would this potentially be a product for the future? It is already an enzyme that is currently sold by Chris Hansen. They developed it in partnership with Novozymes, and it is available. The product is called LactoYield, and its main application has been lactobionic acid production, so complete conversion of lactose to lactobionic acid. And we've been kind of the group spearheading, looking at it as a potential natural antimicrobial in dairy systems. So are there any other questions from the crew? If not, that's kind of our work here. Hope it's been interesting.
Wow, thank you, Sam. That was fantastic and so engaging. I hope everybody has got a lot out of it. But if you have further questions for Sam, he's included his email address there on the final slide, and you can contact him directly. So with that, thank you, Sam, for all the work you've put into this amazing presentation, and we look forward to future liaison with you and keeping track of what you're doing in the future.